In this video, we're going to focus on establishing or proving trigonometric identities. So establishing or proving trigonometric identities means checking or verifying if one side of an equation, right, that involves trigonometric functions is indeed the same as the other side of the equation or is equal to the other side of the equation. Again, that involves trigonometric functions like this equation. So what we need to do is to manipulate either the left-hand side or the right-hand side of the equation and see if we can convert it or transform it into an expression that is the same as the other side of the equation. Okay, for instance, we can manipulate the left-hand side of this equation and then check if it will result to the same expression on the right-hand side of the equation. Okay, now in order to do that, we need to apply some common trigonometric identities. All right, so before you continue with the video, be sure to review some common trigonometric identities, such as the reciprocal identities, quotient, Pythagorean identities. We also have double angle, power reducing, and sum and difference formulas, so on and so forth. All right. Now we have some guidelines that will help us in dealing with these kinds of problems. So first, choose one side of the equation. It is preferable to pick the side that is more complicated and transform it into the expression on the other side of the equation. If both are equally complicated, start with either side. By more complicated here, meaning does one side of the equation contain more factors than the other side, or does it contain fractions, or does it contain higher powers, so on and so forth. Okay. Number two, use algebraic techniques to manipulate that particular side of the equation. Algebraic techniques like expressing sums or differences of fractions as a single fraction, okay? Apply factoring, apply special products. We can also apply a rationalizing technique, all right? Multiplying conjugates, so on and so forth, if they are applicable, all right? Then we have here, of course, we use appropriate trigonometric identities whenever they are applicable. Okay. And then lastly, expressing in terms of sine and cosine functions only is usually helpful. This is because some of the or most of the common trigonometric identities that we know that we are familiar with are in terms of sine and cosine functions. And so in turn, we can easily manipulate them. All right. Now let's try some examples. First, let's take, for instance, the equation that we had earlier. Cosecant theta times cosine theta equals cotangent theta. As you can see, the left-hand side of the equation is relatively complicated compared to the right-hand side of the equation. Okay, and so we start with the left-hand side. We manipulate it, we convert it to or transform it into an expression that is similar to the one in the right-hand side of the equation, which is in this case cotangent theta. Okay, we can start by applying an identity for the cosecant function. Remember, this is the reciprocal of the sine function, right? So that we can write it as 1 over sine theta. Okay, so 1 over sine theta times cosine theta. This gives us cosine theta over sine theta. This ratio actually is equivalent to cotangent theta. And so we established the identity. All right. Next, let's try this one. We have 1 minus sine theta over cosine theta equals cosine theta over 1 plus sine theta. Now, since both sides of the equation are relatively the same, they are of the same level of complexity, if you will, then we can start with either side. We can opt for the left-hand side or the right-hand side of the equation. Say in this case, we start with the right-hand side of the equation. Okay, we can actually try to express the left-hand side of the equation as sum of two fractions, right? That would be 1 over cosine theta minus sine theta over cosine theta, where 1 over cosine theta is secant theta, and then sine over cosine is tangent. So we have secant theta minus tangent theta. However, we cannot do the same to the right-hand side of the equation. Okay, we cannot express this fraction as sum of two fractions as readily as the left-hand side. Okay, and so we have to try another approach. Okay, for this one, we can apply multiplication of conjugates. Okay, so we have here 1 plus sine theta. We can apply or we can multiply an expression which is equivalent to 1 that involves the conjugate of 1 plus sine theta, and that's 1 minus sine theta. Now, why are we doing this? This is for us to generate an expression for which we can apply an identity. All right, because as it is initially, there are really no identities that we can, or appropriate identities that we can use. Okay, and then why did we opt for applying conjugate? This is because if you look at the Pythagorean theorem, okay, initially that's sine squared of theta, say theta, plus cosine squared theta equals 1. Okay, if we isolate cosine squared theta, this becomes cosine squared theta equals 1 minus sine squared theta. The right-hand side of the equation, this expression here, is a difference of two squares that is factorable by the factors 1 plus sine theta, 1 minus sine theta. Okay, we have here 1 plus sine theta. If we multiply this expression to 1 minus sine theta, for this one, 1 plus sine theta, 1 minus sine theta, this results to 1 minus sine squared theta, which is ultimately equal to cosine squared theta. Okay, so let's continue multiplying. In the numerator and the denominator, we have cosine theta 1 minus sine theta divided by 1 minus sine squared theta. Again, 1 minus sine squared theta is equivalent to cosine squared theta. So this becomes cosine theta times the quantity 1 minus sine theta over cosine squared theta. We can now cancel out cosine theta, 1 cosine theta, and so we have established the identity. Next, let's try this one. We have sine of alpha plus beta divided by cosine alpha times cosine beta equals tangent alpha plus tangent beta. For this one, we can manipulate the left-hand side. All right, we can start by applying uh, an identity or converting sine of alpha plus beta into its sum of two angles identity. And it's equivalent to sine alpha cosine beta plus cosine alpha sine beta. Again, this is from uh, the sum of two angles identity of sine. All right, and then from here we can express this fraction as sum of two fractions. All right, and this gives us sine alpha cosine beta for the first term divided by cosine alpha cosine beta plus, for the second term, this one, cosine alpha sine beta divided by the same denominator, cosine alpha cosine beta. Cancel out common factors. For the first term, cosine beta cancels out. Second term, we can cancel out cosine alpha. Okay, and so this can be simplified as the sum of sine alpha cosine sine alpha divided by cosine alpha and sine beta over cosine beta. And then from the ratio or the quotient identities, we know that the ratio between sine and cosine is the tangent function. Okay, so for the first term, this is actually equivalent to tangent alpha. Second term is tangent beta. All right, and so we have established the identity.